So let us continue from where we left off in class. If you saw the previous video, this is going to be more or less the same, and then some more. So let us cover Theorem 9.1 first. Theorem 9.1, which says if f is differentiable at a, then f is also continuous at a. F differentiable at a implies f continuous at a. And the proof is relatively simple. If you think about what is happening, differentiable at a means the limit of x approaches a, f of x minus f of a over x minus a exists, right? We don't know what the limit is, but we could call it some letter, call it c. Okay, so there is some letter, some number c, which is the limit of this, right? And it's finite. Therefore, limit x approaches a of f of x minus f of a, just this much, is equal to limit x approaches a of c times x minus a, which is equal to c times limit x approaches a of x minus a, which is equal to c times 0, which is 0. Therefore, limit x approaches a f of x is equal to f of a, and that means the limit as x approaches a f of x exists and is equal to the value f of a. Therefore, f is continuous at a. Therefore, f is continuous at a, proving our statement of the theorem, right? Now, we know the other way is not true. You have seen the counterexample quite a few times. F continuous at a does not necessarily imply f is differentiable at a, right? The standard counterexample is something like this, and that's my point a and f of a, right? This function is not differentiable at the point a. Now, can I make a function which is, can I find a function, find f which is differentiable nowhere but continuous everywhere, which is continuous everywhere but differentiable nowhere? Okay, and we can try. Of course, I can't really draw the function because you will see why. Okay, so the idea is going to be like this. First step, take your original function, which is not continuous, which is continuous everywhere, but not differentiable at this one point a, right? Now, my function still is continuous on this line as well as this line, right? And it is also differentiable on them. I want to make sure it is not differentiable on those points. Well, the idea is I am going to add a jagged edge there, right? Instead of having a plain edge, I'm going to make it jagged. This way, I have added two more points of two more points where it's not continuous, differentiable, right? At these points, it's no longer differentiable, right? So instead of having one point where it's not differentiable, now I have 3 points. Next step, it's still differentiable on the straight edges on each of these parts, 1, 2, 3, 4, 5, and 6. And so I make each of them also jagged. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Again, by doing this, I am preserving the continuity. The function is still continuous everywhere, right? But now I'm adding more and more points where the function is not differentiable. And so if I repeat this process infinitely many times, I am going to get a function which is continuous everywhere and differentiable nowhere. Okay? So, but this exact function is hard to draw, and writing a good form of this function is really hard. We can make functions oscillate pretty much nicely with functions like f of x is equal to x sine, let's say 1 over x, and 0 at x is not equal to 0, x is equal to 0, right? We have seen that this function oscillates a lot, but we have no idea about its derivative, and this function is going to be continuous everywhere else other than 0. At 0, we have a problem. We don't know if it's differentiable or not. We know that it's continuous because we did it before. So we will explore such functions later. The function that I mentioned up here, this function is going to be accessible only after chapter 24. But till then, let us first look at this function. Okay, example. Let us try to find f prime at 0. Does f prime of 0 exist? Well, f prime of 0 is equal to limit x goes to 0 f of x minus f of 0 over x minus 0, which is equal to x sine 1 over x minus 0 all over x minus 0 is just equal to, limit x goes to 0. This is important. Please do not forget, like I just did. Limit x goes to 0. X sine 1 over x, these cancel, is equal to limit x goes to 0 sine 1 over x, right? And we know that this limit does not exist. Equal to d n e. Therefore, f prime of 0 does not exist, and f is not differentiable at 0. Okay. Well, we can try to argue the exact same way and try to find the derivatives for the following functions, which I'm leaving for homeworks. The proof is going to be exactly the same, but you will be able to show that these functions might just be differentiable. Sine 1 over x, x is equal to 0, x is not equal to 0, or second, f of x is equal to 0, just sine 1 over x. X is equal to 0, x not equal to 0. Okay, try both of these functions, see what you get. Okay, those are homework exercises, and I will stop this one here, this video here.